You were? Nice, girl.
Okay, it's time for silence. No one talking. Derek, look up. You're good. No one talk. Okay, I can't use L'Hopital's rule unless I have a ratio. Something divided by something. You don't always use L'Hopital's rule when you're trying to solve a limit problem. In fact, I would have probably first looked at the limit and said, hey, can I factor and divide? But that's not going to work. Next thing I look for is h approaching infinity? Then I can look for terms that are adding and compare them. That's not true. So L'Hopital's rule is a good option. So I must first do the test. Again, to do the test, I have to have a top and a bottom. So I basically said multiplying by 1 over h, that's the same thing as simply dividing by h. Questions to that? So now I do the test. Step number 1, test. So I plug in h equals 0. Let's see, so that's the natural log of 2 plus 0 divided by 2, all divided by 0, which is the natural log of 1 divided by 0. The natural log of 1 is 0. So this test was successful in terms of L'Hopital's rule. Questions to that? Happiness there. So next step is to find the derivative of the top and the bottom. So we go step number 2 here. Find the derivative of the top and the bottom. So I take the derivative of, and we always differentiate in terms of the limiting variables. In this case, that's h. Derivative of natural log of 2 plus h all over 2. That's equal to, the derivative of the natural log of something is 1 over the something multiplied by the derivative of that something. Pause there for questions. Okay, this one can be written in a much simpler way. Somebody pick up the ticket and tell me how to write this in a more compact form. Right, please.
Instead of 1 over 2 plus h, what does it equal to 1 over 1 times 2 over.
Nicely done. So Heidi remembers that dividing a fraction means multiplied by that fraction's reciprocal. So we're going to do like that. That's going to clean up nicely. This derivative can also be done a lot quicker if we just do one thing before we actually try to find the derivative. Jackson?
We pull up a 1/2.
Nice. The 1/2 is really just a multiplying constant. So this is going to be 1/2 multiplied by d of 2 plus h. Take it for Heidi and Jackson. Questions? Please. So dividing by 2 is the same as multiplying by 1/2. So we can pull out the 1/2 multiplier. Questions? You, Ellie? Anyone else? Please.
So if we were just to find the derivative of d2 plus h over 2, would it just take longer? Could you still get it right?
Yeah, totally legal. It just takes longer. So whenever I see a quotient and the denominator is a constant, I always pull it out. It saves me using the quotient rule, prevents some mistakes, that sort of thing. But totally legal. So you can take it for ready. So keep going. Oh, somebody clean this up. This cleans up rather nicely to something more compact. Please. Not quite 1 over h. Tell me why you thought that. I want to fix your mistake.
I thought the two just,
These here.
yeah.
Remember that this division is not legal because this is not two things being multiplied, it's two things being added. You can only divide factors or terms that are multiplied, so that doesn't work. Take it though, Heidi.
This is times 2 divided by 1/2, so 2 over 4 plus 8. Or
You can do that.
4 plus 2.
Take it for that for sure. Here's what I was thinking. If I were to multiply these, it's going to be this times this times this. So the order doesn't really matter in multiplication, so I'm going to do this instead. Okay, please show me 1 or 2 if that makes complete sense to you, that these are the same. Well, 1 or 2 if that makes complete sense. That this is the same as this. I haven't dealt with the other part yet. 1 or 2 if this is the same as this. Cal? Okay, I can't see as well as this. Okay, you're good. Landon? Good. Questions, anybody? Cool. So these divide to make one like that. Okay? Oh, please.
Actually,
No worries. This derivative is now pretty easy. What's this derivative equal to? Just 1. Question? So all this work, I figured out that the derivative of the top is just 1 over 2 plus h. Questions? Please.
So, I don't know. I didn't put the 2 plus h over 2. I put, when I started, I took the 1 over h and just changed that h to h to the power of -1. Could I still do it that? Could you do it that way and still get the right answer? I got the right answer.
Yeah. Should work okay. Technically, I would go with the case of, create a numerator, create a denominator, take the derivative of the top, derivative of the bottom, but it should work okay. Anybody else? So now we do the next step. So we scroll up here. Step 3. Step 3 is find the derivative of the denominator. That's just h, so dh over dh is 1. Step 4 is create the new limit problem. Derivative of the numerator was 1 over 2 plus h. Derivative of the denominator was just 1. Step 5 is to test again. H equals 0. So you end up with 1 divided by 2 plus 0. Final answer is 1/2. Questions? Please.
If this is on the test, would it be FRQ? Or would this one say that always be okay?
Great question. I'll give you 2 for that one. I've never seen it on an FRQ. I mean, they won't, but I've never seen that.
Okay.
Anybody else? Cool. You else bring a question with them to class? Good.
I just have a general question. So, as I was doing homework, I was talking to somebody who's in a little further ahead in their math class.
Sure.
I think they're in DCH out. And so with the limit problems, I'll find it. Like number 2, the limit problem, it has. So it has that, and as I was talking to him, he told him that his teacher told him the second half of the top of the numerator you can ignore because it's a constant, and with limits, it won't matter, and so you can just ignore it and just focus on the h 1/2 plus h to the 1/2 plus h to the 8, and ignore the negative h to the 1/2 to the 8.
I personally I'd like to hear the teacher's argument as to why that will always work, because it works in this case, but I can think of some examples where if I told a student to do that and they followed my directions precisely, they get the wrong answer. Like that other term would actually make a big difference. So I would never want to say that generally.
Okay.
So I'd have to talk to the teacher and find out why he said that. But good question. Take it, Kelly.
Oh, thank you.
No, it's really a question, Chance. This case it does work, but in general, I wouldn't ever say, oh, because that's a constant, you don't have to worry about it. Like I can actually create a limit problem pretty quickly that's the opposite. The constant is the important part. Okay, so. Well, in the case of L'Hopital's rule, it works just fine because you're going to take the derivative of the numerator. And yes, when you take the derivative of the numerator, the additional adding constant is just going to be a derivative of 0. So it works with L'Hopital's rule, but not in just limits.
For L'Hopital's rule, no.
You're taking the derivative of something, and the derivative is this plus this, and this is a constant. Yeah, the derivative of constant is always
So I think that's what,
maybe that's what he meant. The first thing I noticed, first thing I noticed is that if I rewrote it like this, I do create two functions being multiplied, which means u substitution is a possibility. Trouble is, if I choose x squared plus 1 to be u, the derivative of my choice would be 2x, which isn't the other multiplying function. Question? So that doesn't work. Something that works all the time on these problems is if I can change this integrand into something that's being only added instead of something that's being multiplied, then I can find the antiderivative. So if it's easy to just multiply it out, just do it. Please.
So on the antiderivative rules, I have the one that is ax plus b to the n dx. And the reason that doesn't work is because the x is squared, so it has to be the exact same as this.
Perfect. Daily.
Can you separate it into 3 different ones? Can you do it like that?
Tell me what you mean by 3.
Like, since they're like added, so you can, I don't know, like you do like the antiderivative of x before plus the antiderivative of 2.
Oh, yes, sorry, I misunderstood. Yes, that's the whole idea. Once I get this, it's called the integrand, the thing we're finding the antiderivative of. Once I get this as just separate terms being added, you can completely find the antiderivative of each separate term.
But why did you say the antiderivative?
Oh, he's looking at this. He's saying, hey, this looks a lot like the antiderivative rule that says ax plus b to a number, but because this is squared, that rule doesn't work. Questions here, please?
so I have another question. So on problems that you're finding the derivative of a problem with an integral, so the way you do it is you use the equation and plug in both of the limits on the integral, right? And so when you plug in dx, you plug into the integral, and then do the integral of just x, and then you do the same thing with the limit of whatever the number is, 0, 1, 2, whatever. And then when you do the derivative of that, isn't it always going to equal 0? So it's going to cancel that part out. I mean, make it equal 0. Hold on. Does that make sense?
Yep.
Will that always work?
I know how to answer your question, but it'll help me out something about me, so you're good. So here's an example of what you're talking about. So taking the derivative of this integral, and what everyone look at this, it's a good question. Hey, look up. It fits really well with what happened on the AP test one year. It's a really good question. The AP test writers are really smart. They know that everyone looks for patterns, and so they are always finding ways to disrupt the patterns. So here's what they did. They had the test several years in a row, and they released the test, so we get to all look at them. And you get to see them and everything. And so you start to notice a pattern. It's the pattern that Chance is talking about. That when I'm finding the derivative, I'm taking the last step here is to multiply by the derivative of the lower limit. And he said, hey, every problem we've done so far, the lower limit's always been some constant, like 0 or 1 or 2. Therefore, this derivative is always 0. 0 times this is 0, it's just gone. So you kind of get in the habit of saying, maybe I just can always ignore that. Okay, and guess what they do the next year? And they did this. They switched the limits. Okay. They put the x squared here. Okay. But you see why they do it, right? Yeah.
But that will still work just so long as you can recognize in your head that they switched it.
Yeah. You just follow the rule, right? So now this becomes 0.
Okay.
Yeah, and this one doesn't disappear. And then I would expect them some year, Chad, to do this. Again, they're just looking for ways to disrupt the pattern. They're testing, do you really know the formula or not? So they put an x here and an x squared here. And now neither one disappeared. But just follow the rules.
Just head.
Yeah. Make sense?
But so long as there is a constant.
Oh, the constant, the derivative is for sure.
Okay, so something similar to that on question 38.
First period, I got I couldn't do it. The motion picture.
I found that, yeah, the
I must have made a mistake. 38? Hold on. That's not really likely to happen on questions that they give us, so let's just take a look. So right here is where Mikkel is talking about. I'm taking the derivative of the numerator in terms of h. It is related to what Chance asked about. The numerator is 2 terms being added. The second term, cosine of pi over 2, don't worry about what value that is, but it's some number. So I've got 2 things being added, so I can take the derivative separately. And the derivative of a constant is always equal to what? 0. But I still must take the derivative of this. So the derivative of the cosine of something is sine of same something multiplied by derivative of the something. And here I've got 2 things being added again. So Mikkel, what's the derivative of this constant alone? 0. But that would be plus dh over dh, which would be a derivative equal to 1. And then 1 plus 0 is 1. So this whole piece becomes 1. So I really don't get 0. Does that help? No, good question. Anybody else? Anyone else bring a question with you to class? Please do. 33. Very similar, actually. Look up. Okay. We could try and do a u substitution. The first thought of doing a u substitution would be to rewrite this like so. X to the 1/2. Oh, sorry. Oh. Things like, I'll do it. Thank you. No, you're good. 33 wasn't actually in the homework, but it did show up on a problem in pink, looks just like it, so it's okay. The choices here would be u equal x, not a good choice, or u equal x plus 1. Problem is, if I take the derivative of this, I get 1, and that doesn't match the other multiplying function. So u substitution's kind of a dead end. But remember what I said a little bit just moments ago. If I can find a way to change the integrand into just several terms that are added, that will always help. So if I distribute, it's going to help. So I go this times this. Let's see, that's x to the 1/2 multiplied by x to the first. But x to the first is really x to the 2/2. Excuse me. And then plus x to the 1/2. So I successfully split it into two things being added. Questions to that? When these two terms multiply, the exponents add. So it becomes x to the 3/2. Plus x to the 1/2. X. Question? Hopefully it's sort of.
I'm like confused, like how we got those exponents.
No worries.
I just don't see where they match up to. Like I get the x to the 1/2 is the same as the square root of x, and then the x 2/2 is like x to the first. So I just use x. I don't like where's the one, like the plus 1 coming from? Like where does that go?
The plus 1 here?
Yeah.
Oh, no worries. I distributed. So it's this times this,
Okay.
plus this times this. So x to the 1/2 multiplied by 1 is just x to the 1/2.
Yeah.
Is that your question?
Yes. Okay.
You're good?
Yeah.
So keep asking tickets. Please.
So in the first green one, you didn't distribute the x to 1/2 and x 2/2 together, right?
Right, I wrote it.
Saying that you're multiplying.
You got it, perfect. I'm saying this needs to be multiplied by this. And to just make sure no one got lost as to what really happened, I just wrote them next to each other. And then I said, oh, how do these multiply the exponents out? That's a good question. Take it. Anyone else? So now it's time to find the antiderivative. I just use the antiderivative rule. Question? So when I do this, question? Cool. Okay, dividing by a fraction is the same thing as multiplying by that fraction's reciprocal. So I'm going to rewrite this as 2/5. So 2x to the 5/2 all over 5 plus 3x, no, 2x to the 3/2 all over 3. And evaluated from 0 to 1. Questions?
Wait, how did you get that?
So whenever I have something divided by a fraction, that's equivalent to the something on top multiplied by the reciprocal of the fraction.
Okay.
Yeah, good question to your fluency. No? Now at this point you can take a shortcut. So I want everyone's eyes on the board so you can see the shortcut. Because you'll like this, it gets to be kind of a pain to keep writing everything. So just do a little mental, quick shortcut. Look, I'm going to plug in 1 to start with. Okay, but then I'm going to plug in 0. 0 I always kind of catches my eye. Because what's 0 to any power? Say it. 0. So what's this going to be? 0. What's this going to be? 0. You don't have to write any of that. Just, you know it's 0, it's great. One's pretty easy too, though, because what's 1 to any power? 1. So really, all you have is 2/5 plus 2/3. Now you have to do some fractional addition. That's wrong, isn't it? What's it supposed to be? And the other one is, there we go. Ah, come on. Who's pressured the board? Okay, thank you. You're very cunning. Awesome. Kindness is a virtue. All right, so please, Gladys.
So, when you're evaluating it, you plug in the 1, but I don't understand how you multiply, you put the 1 in for the x, and then it turns into 2/5, but where did the 5/2x from go?
Gotcha. So I put it in for x first.
Yeah.
So the first thing I have to do is take 1 to the 5/2 power.
Yeah.
But 1 to any power is just 1.
Oh, you're right, okay.
No worries. Does that answer your question? No, your question. Take it. It's quite the contrast. The hat, the coat, the shirt. It's like a commercial.
Hospitals are still friends.
Yeah, there you go. LaBelle Edwards and Ron McBride. So, all right, very nice. Nobody knows who that is. Jackson knows. Oh, LaBelle Edwards and Ron McBride.
How do you not know that?
He did. All right, new stuff. Here we go. You looking there at 30 plate? Oh, sorry.
So like Tuesday's ACT.
Gotcha. Here's what will happen. Look at me. Hey. Hey. I asked a good question. So on Tuesday there are no classes. No, there's no classes. So as soon as I'm done, I am required to help with the ACT. If I could somehow find a way to help you instead, I wouldn't do it. You know, like instantly. Don't say I don't like it. So. But it's very true. Like I would much prefer to just say I'm in my room, students come, and I will help all morning. But I'm supposed to help with the ACT. So.
What about if you accidentally send your student to another room?
Yeah, that would be a termination offense. Like I actually have considered going to a third career now that I've spent 15 years in one and 13 years in another. It seems like about time to change again. But
might as well.
if I decide to, I feel like one of my terms.
What do you
I thought of going back to software development. Just to figure it out. Dabble a little bit.
Testing the
So it's Wednesday and
Wednesday is a P day.
you got to freaking
The test is on your
Hey, quiet. Look at me. Look at me. Look at me. Sarah, look up here. Okay, so what will happen, what I'll be doing is I can stay pretty late on Monday, and I can stay pretty late on Tuesday. So as soon as the ACT is over, I'll be back in my room. What time is that? I believe, you're good. I believe, based on previous years, that I should be back in my room by noon. If I get done sooner, I'll be back sooner. So if it's a few minutes later, just wait patiently, I will return. I can stay pretty late on Tuesday, So, and then the test is on Thursday. Yeah, to address Sarah's question, they actually was suggested several times, like, hey, why don't you just change the A/B schedule to just, make Wednesday an 8A? Would make more sense. But the reasoning was, the claim was we have too many students who attend middle school who take high school classes, and it messes them up. Like, well, just make the middle school change. Whatever. Here we go. Look up. Oh, please.
Don't be that guy.
B-Day will just get an extra day for that question. B-Day just gets an extra day. Hey, look up. Go back. Do that some more. Look at the more. Look at number 30. Come on. No, brand new problem. Brand new problem. So new stuff. Okay, you're good. Okay. Can't talk now. Brand new, you gotta concentrate. Brand new idea. You gotta really turn up your concentration a bit. Okay, this is a specific type of problem. It's known as a related rate problem. Okay. Now, to kind of help, I'm going to do what I did last time. I'm doing a different example in this. We'll probably get 2 or 3 examples. I'll do different examples in this class period than I did in first period, so that if you need to look online, you get a little extra help. Related rate. Write that word down, please. Related rate. Okay. You can tell it's a related rate problem when they describe a situation where there are at least 2 rates that are somehow related to each other. Let me give you a counter example. Okay, you did a problem on the test where it said there was a container of sewage, okay? And there was a rate at which sewage came into the container and a rate at which sewage left. Well, that's 2 rates, but those rates aren't really necessarily related in any way. They're just separate, they're independent. Like the rate at which it comes in, the rate at which it leaves, they don't have to be linked. Do you understand? Okay. The difference here is they're talking about a circle, okay? And so the circle, I'll do my best to illustrate with my hands. The circle grows, it gets bigger and bigger and bigger. It says the radius of a circle is, oh wait a minute. As the circle grows, what's increasing? Help me, just say it. The area inside. So the area grows, what else? The diameter grows, what else grows? The radius grows and the circumference, okay? Now, hey, look at the circle. Look, hey. As the circle grows, all of those rates are related. Fair? Like there's some way that the amount that the area grows is going to be related to how fast the circumference grows. It's not like the tank, where the 2 rates are unrelated. That's what we mean by related rate. The good news is this. At the end of first period, I had them look through a series of problems. They said identify the ones that are related rate, and they could all do it. So identifying a related rate problem isn't very difficult. As you read the problem, you go, oh yeah, this is related rate. Sort of, please.
Well, like, from what you said, it sounds like it's a ratio, kinda, because like the way the circle like moves, like they all like are a ratio to each other. So is that like kind
They don't actually end up being a ratio necessarily, but it is the right idea, that there's some sort of relationship between them. But you're right on the right track. It won't necessarily be ratios though. Okay, next thing, write this word down for me. Write that down. So the apostrophe is there for a missing letter. You'll hear about the missing letter in a second. So this little acronym is extremely helpful when you're solving a related rate problem. Haley, question?
Well, I was saying the circle, like, it's all the things that's together, aren't they all like the same rate?
Oh, your intuition would make you think that, but it isn't true. The rates are different. And I can't show you why in just a few moments. It would take a bit of computation to illustrate, but they really are different. Hey, look up, come on. Okay, this acronym is really, really helpful. When you encounter a related rate problem, the first thing you do is write down this. And then just follow the instructions. Here are the instructions. The first part here stands for, well, first period is what I really did. In first period I wrote this. And I said that the R stood for write down all of the rates. Okay, come on. Write down all of the rates that you read about.
It's a lot of R's.
Yeah, that's why it's R. Okay. Write down all the rates that you read about. And write down all the rates. This really helps, I promise.
Did someone make this up?
Yeah.
Yeah.
I didn't make up this one.
So do you have a?
They didn't leave a poster.
Who made it up?
You can picture her face. She sat right there. Savannah Norton. It's been a long time.
Wow, that was good.
I tried. Gotta leave a picture. Picture, you know, you go down in history. So.
Yeah, I know.
So anyway, write down all the rates that you read about. The suggestion in first period was that since you don't spell right with an R, that they put a little apostrophe here to indicate the missing W. But anyway, it's up to you. I said just talk like that guy in the Princess Bride, the priest, just say, write down all the weights. Okay? Marriage. Look up. Gotta move a little quicker. Okay, so you write down all the rates that you read about in the problem. So someone raise your hand and tell me what is one rate that you are reading about as you read the problem, and you're trying to write down all the rates, and I'm trying to use as many R words as I possibly can to emphasize the fact that you are writing down all the R rates and the rates and the breathing and never mind.
Riemann zone.
Like Elmer, butt up here. I know Elmer Chase, but never mind. Good. The radius of a circle is increasing at a non-zero rate. Okay, next thing, watch me. Hey. So R is the symbol that represents the radius. It's very much like the last test. I kept emphasizing in all these problems there's an amount and then there's a rate. Well, R is the amount. It's like how much the radius is. But there's a rate at which that radius is growing. So we need a symbol to represent that rate. So we happen to know the symbol, the mathematical symbol that will represent the rate at which the radius is growing. Our hands, come on. What is the mathematical symbol? Nice. So we write down that rate, DRDT. Take it for city. DRDT is the rate at which the radius is growing. Question? Keep reading. It cannot be a related rate problem unless there are two rates that are related.
Area.
So let's see here. The radius is growing at a non-zero rate. At a certain instant, the rate of increase in the area. Nicely done. So what would the symbol be?
R-A, R. Where no, D-A-D-T.
Nice, ADT. What was that? So DADT. Question? We keep reading. They do mention another rate. So Thomas, how do I say that here? DC over DT. Questions? For Derek? Pretty good? Okay, we've done the first thing. We've written down all the rates. Okay, E. E stands for equation. And the reason we write down the rates first is by looking at the rates, we get a clue as to what equation we should also write down. So it's again back to that idea of paying attention to the difference between amounts and rates. The amounts, or the quantities described in each of the rates, are radius, area, and circumference. So circle those on your paper to remind you of something. So the amounts are the radius, the area, and the circumference. Therefore, we need to come up with either one equation, and in some cases, two. I've never encountered an AP problem where you would have three, but theoretically that's possible. We need two equations or one equation that contain R, A, and C. So now you have to pull from memory your knowledge of circles.
Would it be pi r squared would be one of them?
Very good. So I write down the equation, pi r squared. That works perfectly for an equation that contains an R. And I've got to have it equal to something, Landon. So what's this equal to?
That would be
Area.
Not area. It would be area.
Ah, great comment. Look up. Hey, take it for Landon. I've always noticed that everyone always remembers pi r squared and 2 pi r, but they tend to have trouble remembering which goes with circumference and which goes with area. Here's how you remember it. Area is measured in square inches or square feet. Therefore, this has got to be area. Circumference is measured in inches or feet. Therefore, circumference is just 2 pi r. Questions? Cool. So we have two equations. Hey, sometimes you'll only have one. But we have two equations. The equations have what we need. They are equations that contain the R, the A, and the C. Please, Hayden.
So you said you're supposed to combine them into one equation and all three.
Oh, I said that, I misspoke, so apologize. So ideally, I'd like to have one equation, but sometimes I just can't. Sometimes there's just two to work with. So. Anybody else? Awesome. Step 3. I wrote a small d for a very specific reason. Instead of a capital D, say it louder.
I wasn't saying anything related.
Oh, never mind. I said the right word. Apparently not. Turn bright red back there. So why did I write it? Why did I write? No, apparently not. Why did I write a small d? Somebody. Lots of smiles. I'm just clueless, but whatever. Okay. Questions? Help somebody. They have an idea what D stands for? Please.
Determine.
Determine's a good guess. Derivative. Yeah, because the symbol for derivative isn't capital D, the symbol for derivative is small d. So derivative, right? Okay. So the next step is to take the derivative. Now look, hey, look at the acronym. Notice how the letters work together. We write down all the rates that we are reading about, okay? We come up with an equation based on the rates. The reason for that is this. The only way you can have rates that, this is back to Soren's comment, the only way you can have rates that relate are if the original quantities also relate. So the area and radius are definitely related. The area, the circumference and radius are definitely related. That's the only way the rates end up being related. D says take the derivative of the equations with respect to time. So right here we're going to do derivatives. So we take the derivative of both sides. D over dt of A, d over dt of pi r squared. Do the same thing here. D over dt of C, d over dt of 2 pi r. You can't set them equal unless there's a reason that would allow that. So don't do that. That would be kind of a blind step. Don't do that. There's got to be a reason. Got to be a reason. But we need to finish the derivative. So the left side just stays dAdt. But the right side can be written differently using the derivative rules. Someone help, please. Deborah. Super close, just one little thing. So we pull out the pi. The derivative of r squared dt is you bring down the 2. Multiply by the r. The new exponent becomes 1, but there's a piece here that we didn't write. dr over dt. Take it for Deborah. Question? Don't forget the dr over dt thing. That's the most common error. Somebody do the other one? Please, Sarah.
Can't take out the 2 pi.
So this side is just dc dt.
Yeah.
We'll have the 2 pi, which is a constant.
And then it's just dr.
It's d over dt. Take it for Sarah. Okay, at this point, we're done with the acronym, and it's as though we are starting the problem from the very beginning, but to help us solve the problem, we have some new information. So it really is like we are starting the problem from the very beginning, but to help us solve the problem, we have this new information here. So let's see. The radius of a circle is increasing at a non-zero rate. A certain instant, that word instant is important. So I need eyes over here now. Look at this other, rotate, look to me, look at me, look at me. Okay, that word instant is important. Here's why. The circle's growing. You're not really ever answering a question about what's happening like as the circle grows continuously. You're answering the question about a certain instant in time. It's like some people call it like a freeze frame moment where you like take a picture. The circle keeps growing, but you're going to identify what's happening at that instant. So the instant is very important. So it says at a certain instant, the rate of increase in the area is numerically equal. Hey, somebody said set them equal to each other. The rate of increase in the area of the circle.
You don't get that. Definitely did not.
The rate of increase in the area of the circle is numerically equal to the rate of increase in its circumference. So there is a reason. Now look, it's only at that instant. Hey, this is back to Haley's question. Those rates are not always equal. Like dAdt is not always equal to dCdt. But they tell us that at one moment, just one freeze frame moment, they are. So we need to use that information. At this instant, what is the radius? So that's why we really do want to set these two equations equal to each other because of that clue. That clue isn't going to show up on every problem, it's just this problem. Questions? Please. There will be some other clue that will guide you as to where to go next. So you follow the acronym until you get to this point. And then what you really do, Haley, is you say, I'm going to start all over, but now I have some new clues. And you use the problem itself along with the new clues to figure out what to do. So here we go. Did you say boom, baby? Second time today, popular phrase.
Oh, yes.
Popular phrase today. First period. So I'm making a list so that when my grandchildren get older, I can go back and talk to them. Like, yeah, our grandpa is the coolest, man. This old gray-haired guy, but he talks just like us.
Dab on.
Grandpa can dab and everything, man. Nay, whip, all that good stuff. Okay.
Show us the mechanics of it for us.
I'm working on it. Working on it. Wake up. Hey. What's the goal of the problem at this point? Somebody help. Yeah.
To solve for R.
Solve for R. So take it for Landon. Somebody suggests what we might do at this point to solve for R. Deborah's in, Sarah's in, Bailey's in. Let's go. Soren's in. Let's go. Braden.
You divide by pi times 2, or 2 pi, or whatever.
Sure. So we take this half of the equation, divide by 2 pi, which means we must do the same thing on the other side. More slang here. Yeah, that's universal. They've been saying that for hundreds of years. So now what? Somebody, please. What's that?
Why are you keeping the BR of DT?
Oh, I have to. The clue said that the rate of increase of the area at a certain instant is equal to the rate of increase of the circumference. So what they basically said was that dAdt is the same as dCdt. So that means that since dAdt is this, including the dRdt, and dC, I pass out, please call this out first. dCdt is this, they have to equal each other. Like they have, I can't get rid of it without doing something mathematical. It all depends on the problem. The thing to keep in mind, really, Haley, you're asking the right question. The answer is, though, you follow the acronym, it gives you some new clues. From that point, the problems will differ a little bit. And so you just kind of have to learn to use whatever clues they give you. Technically, I think it's better to do what I'm about to do. So, hey, hold on a second. Hey, come on. You want to talk? Quiet. Come on.
Is it still like dr over dc because you don't know what r is?
Remember this. Hey, come on, look up, look up. This doesn't mean d times r. It's dr dt. So r isn't here at all. It's the rate of increase of the circumference. It's not, has nothing to do with me not knowing r. It's like I don't know what dr dt is. So make sure you keep that separate.
So you,
Go ahead.
why can't you find the derivative of it?
There's no information that would allow that at this point. But we won't really need it in this case. Deborah?
Well, can't you just divide it over so it's one?
So let's write what this is going to be first, Deborah. What will this equal?
Yeah, you just.
Oh, these divide out, right? Okay, I feel like we're on two different tracks. Hold on. Take it for Deborah. Is everybody okay? Look, we started with this equation. The suggestion was to divide both sides by 2 pi. That's totally legal. What is the result of the division, Heidi?
RDR over dc divided by dr. Or
Let's see that.
equals dr.
Okay, I want to vote, please. Show me one finger if everything on the board makes perfect sense to you. Show me 2 if you're confused about something. 1 if it all makes sense, 2 if you're confused. Take it for the room. What do we do now? Bailey.
Divide the dr dc over dr.
Yeah, that's what we really do here. We just divide now. Divide both sides by dr dt.
That was bad.
It was bad. It goes back to my talk on the first day of class. We don't say the word cancel, and here's why. Because when people say cancel, they go, look, it cancels. It's 0. Hallelujah.
Nope.
It divides to make
1.
1. So what is r equal to?
1.
Good job, Brady.
Let go of my hair.
Can you turn to 25, please? I barely updated that, so.
Yeah, I noticed.
It's a really good picture. I got to show you this one. It's a good picture. You can leave.
It is. What is that?
Wait, was that like?
This is when you
Oh, that's good. Jared Hansen.
Brought a thing.
What's the fun side of
I mean, not.
There you go. It's kind of appropriate since my son ended up going to Australia on this mission.
No, that's too
It's like his dad's work. It's like he puts something right. It was like his dad's work. It wasn't a pet, it was like part of his life. Everybody works like university or something. Just brought it one day. And again, profile picture. Makes people wonder.
Oh my God. Just imagine just bigger than you.
I'm sorry. No one ever asked. Hey, look up again. Quiet. Yeah, but interesting. So, as a teacher now, the guy brought in the wallaby. That was fun. One day, a kid shows up at the door. One of my students, he's like, "Mr. Smith, go like this." So I put up my finger, and he whistles, and the bird just flies and just lands. Wait. The next one. Maddie Skilling says. Maddie Skilling's one day, she asked me, "Mr. Smith, can I keep my pet tarantula in your room?" I'm like, "What?" She says, "My mom's tired of me keeping it at home. I'm going to take it out to the desert soon, but I haven't had time yet. So and just set it free, you know."
Just put it in the mountains, like.
That's what, you know, anyway, she says, I don't want to get rid of it yet, you know. I'm like, "Go give it a tarantula." Yeah. Her name is Gwyneth. Gwyneth the tarantula. Yeah, it's cool.
Spiders are so.
Yeah, you hold it in your hand, it kind of crawls up your arm.
Snakes, I think so.
Right. Look up. Silence. Come back, my bad. My other one. Look up. Landon, look up. Landon, look up. You're good. Lexi, look up. Okay. Hey, look. Okay, new problem. It's related rates again. Let's work through it. So, red, you need to read the problem, write down all the rates that we read about as we are reading the problem. So one person, please raise your hand, pick up the extra credit. Tell me, Heidi. Yeah, in fact, I'm going to give a little extra hint on this one. They have given this problem many times over the years in AP tests. It's unusual that they give the same problem year after year, but this is one of them that they actually do. And it's the classic street light problem. So a picture really helps. So draw this picture, please. There's a light. So I'm not going to do anything artistic. We're just going to draw the mathematical model. Somebody, hey, how tall is the light? Just say it, please. 8 meters. Put an 8 right here. Okay? The person is walking away from the light. As the person walks away, the distance from the light gets longer and longer and longer. So there's a distance here. Okay? And the key thing is what Heidi just talked about. The problem problem says that the person's 2 meters tall, and he's walking at a constant rate as he moves away from this line, okay? That means as he walks, the length of the line grows at the same rate that he is walking. Let's say that one more time. As he walks away from the lamp, now you'll get it, come on. As he walks away from the lamp, the length of this line, like picture the person being here, okay? Just for an example, if the person is walking 2 feet per second, won't the length of this line also be growing at 2 feet per second? Say yes or no?
Yes.
Okay, good. Other key things here. He's 2 meters tall, so let's draw that out. 6 feet, a little bit more, 6, actually 3, say like 6'6"-ish. The guys who invent problems, they don't care about reality.
Probably the NBA.
Michael Jordan walks away from the street. Okay. Wyatt, come on. Oh.
If he's walking from place to place, and his rate is the same as that's the rate that the
No, it's the same problem again. The rates don't change identically. That's what these problems are all about. Is you have different rates, and the rates aren't all the same, but they are related. And you're. Oh, what I said was, hey, quiet, come on. What I said was this. This line's length, that line is going to grow at exactly the same rate that he walks. Because if he's right here, and this point is moving 2 meters to the right every, no, sorry, not 2 meters, but 2 feet every second, this length here is going to become, it's going to grow at the same rate. Next thing, the shadow is lengthening at some rate. Okay, the shadow's over here. Look at me, come on. Because of how the light works, the shadow's right here. Because the person's body blocks the light, creating the shadow. The shadow's created by no light goes through the person, so you get a shadow here. So draw a line like this, please. So this is the shadow. This is the distance from the lamp. Are you with me? Okay, so we need some labels here. It says at what rate in meters per second is the person walking? So this distance, we'll just give it the classic term x. Okay, what I was saying to Haley and everyone else is, this distance, the rate at which this distance grows is exactly the same as the rate at which he walks. Okay? But the rate at which the shadow grows is different. So we'll call this distance y. Okay, that's how the problem is described. Oh, please, Derek. Oh. Now we need to follow the acronym. So someone please, what is one of the rates that we read about in the problem? Heidi, please. X is a distance, so just convert the x to a rate. Like x is an amount.
So
It's,
could you just do R then?
no, it's a bit easier. You're on the right track. Take it for that. Help yourself.
Would it be X meters per second?
It is, but what's the symbol going to be? What's the symbol? Just dx over dt. Because we want the rate at which x is changing. So x is the amount, dx dt is the rate. So we write down dx dt. If you prefer, you can write this, x prime of t. They mean the same thing, the rate at which x is changing. Take it for Sydney as well. Questions? We good? Okay. Keep going. Sorry, just distracted. Moving on. Agree with me? Yeah. Okay. Are there any other rates described in the problem? Come on, help. Go. dy dt. They give us a value for dy dt, right?
Yeah.
4/9
Yeah.
meters per second. Questions? Okay. Other things are changing in the picture, but we only write down the rates that we read about. Do we read about any other rates? No. So equation. We need an equation that relates those two. This is from geometry, or I guess you guys had secondary one. Is that the class you took? I don't know. Some math class years ago. Similar triangles.
Oh, yeah.
Similar triangles are really, really easy. All you do is compare. It's what Soren was actually thinking about. You just compare lengths to each other. So notice, hey, in this situation, this little triangle is similar to the large triangle. Okay? So because they're similar, the ratios of different sides are relatable. For example, I can say this side is to this side, 2 is to 8. As the similar side on the small triangle, that would be y, is to the similar side on the large triangle, which is x plus y. Questions to there? So I write an equation that relates the quantities described by the rates. What do I do once I have the equation? We're going to take the derivative of both sides of the equation. Here's a big hint though. I would rather avoid using the quotient rule. So can someone make a suggestion that might make it so I don't have to use the quotient rule? Okay, hands up. Who can see it? Come on. Okay, everyone who can see it. What can I do that will allow me to avoid using the quotient rule? Legal mathematical step, cleans things up kind of quickly. Annika.
Changing it to things like y times 1 over x plus y.
Oh, I could do that. Take it for that. There's something even better. Okay. That's what she was thinking, basically. Kind of. Sarah.
Can you multiply both sides by 8?
Multiply both sides by 8. Multiply both sides by x plus y. You get this. 2 times x plus y is equal to 8 times y. Question? I'm going to distribute now as well.
Why are you wanting to do that?
Because before I take the derivative, it would kind of help to make taking the derivative as easy as possible.
Oh, yeah.
Move the y over.
What?
Come on, watch. You got a minute. You got a minute. It's just going to make taking the derivative a lot easier. So now I have this. If I take the derivative of that, much easier. 2x d over dt of 6y. Pull out the 2, you end up with dx over dt. Pull out the 6, you end up with dy over dt. What are we trying to solve for in this problem?
Would the following students please come to the main
What are we trying to
office?
solve for?
Caleb Brown,
Yeah.
Noah
dx
Free,
dt.
Jacob
Do we know what
Newell,
dy
and
dt
Cole
is?
Wilkes. Again, if I could please have Caleb Brown,
You're done.
Noah Free, Jacob Newell, and Cole Wilkes. Please come to the main office.
6 gets multiplied by, what is it, 4 9? And the whole thing gets divided by 2? Go ahead, talk to me. Questions? Bell rang, the question?
Will the following students please come down to the attendance office for checkout slips? Morgan Wesley, Danielle Shenham, Lily Mueller, Casey Huddleman. Again, will the following students please come down to the attendance office for checkout slips? Ryan J. Smith, Michaela Warnick, Casey Huddleman, Lily Mueller, Danielle Shenham, and Morgan Wesley. Please come down to the attendance office.
That's right. That's the point.
Last year, me and Grace made the best. Doing calculus. That was big. Best posted. Our posted was top notch. Not my posted. Yeah, I know. Now you. Oh. What?